Hi everyone, welcome to the low temperature thermochronology course. Today, let's talk about the second section of chapter 6, sample preparation for fission check analysis. This lesson covers 4 topics, including sample collection, suitable minerals, mineral separation, and sample mounting and polishing. Let's start with sample collection. How many samples are needed to collect for fission check analysis? Rocks that are fresh, clean, and ranging in weight heavier than 1 kilogram, depending on different lithologies, should be collected for analysis. For cores or cuttings in drilling holes, which are much smaller than 1 kilogram, it might be possible to combine samples from a range of limited depths. Soil and weathered surface should be removed as much as possible. What kind of information should be recorded for samples? It is critical when sampling to accurately record the sample location, usually with a GPS, such as horizontal datums in latitude and longitude, and vertical datums as elevation or depths. This is particularly important for future users of the data and for databases and modeling. What's the suitable minerals for fission check analysis? Uranium content, track stability characteristics, and mineral abundance were considered to be factors for choosing suitable minerals for fission check analysis. Apatite, zircon, and titanite, which commonly present as primary accessory minerals in many igneous and metamorphic rocks, and as detrital components in some sedimentary rocks, are most widely dated minerals among more than 100 uranium-bearing minerals and glasses. Mineral separation for fission check dating aim at recovering relatively clean concentrates of suitable uranium-bearing accessory minerals. This is achieved by rock fragmentation, crushing, and use of a shaking table, followed by mineral density separation and magnetism separation. A wide-used sequence of this work can be seen as this figure. Let's move to the 4th topic, sample mounting and polishing. Prior to carrying out steps of sample mounting and polishing, if uranium, thorium, helium dating is also planned for this sample, then it is recommended to first hand-pick the best quality grains for that purpose, as grain morphology requirements for helium dating are more stringent. The polishing step described in this section is to establish a flat and well-polished surface in an appropriate crystallographic orientation that results from the removal of sufficient external grain material to expose an internal grain surface for analysis. Monitoring and proper washing should be made carefully, while over-grinding and polishing should be avoided. Mounting processes of apatite grains with an epoxy-only button, Type A, off directly on glass, Type B, as shown in this figure, should follow the manufacturer's instructions exactly with respect to the resin to hardener ratio, curing time, and temperature. Grains in Type A mounts are already exposed at or near the surface, whereas grains in Type B mounts are fully enclosed with the epoxy. Both types of mount can be further processed by grading manually with grate paper on a glass plate before polishing on a rotating lap with different grades of diamond paste. However, an extra time-saving step for Type B mounts is to directly expose target grains prior to grinding by using an automatic cut-off machine. For zircon, the PFA Teflon, which has a higher melt temperature and maintains its transparency even after prolonged etching, has been chosen as the materials for mounting. For titanite, they can be mounted in both Teflon and the epoxy bottom mount as apatite. As the etchant preferentially attacks the highly disordered material in the core of the track, fission tracks can be revealed by chemical etching. The bulk etching rate in materials is not uniform and varies in different crystallographic directions, so that the tracks take on different shapes and sizes, depending on which crystal surface they are etched. Apatite and zircon grains are often prismatic, and during mounting often tend to align on prismatic faces, which are approximately parallel to the C-axis. Over or under etching may jeopardize the quality of data obtained because irradiation damage does not accumulate to any degree in apatite. It is more consistent in its etching behavior, and a standard etching time is commonly used. However, for most apatite grains, it is important to adhere to a strict etching protocol so that key parameters such as track length and depass can be measured in a uniform procedure and reproduced in other laboratories. The correct etching time in zircon and titanite is highly variable and depends on a variety of factors, especially the general radiation damage level, which is reflected in the track density. In general, the degree of etching be judged from the appearance of the tracks and not from the application of some standard etching time. That's all for sample preparation for fission track analysis. Next time, we will have a lesson talking about the external detector method. See you then!